So, reviewing the OBDD definition, this is a binary decision diagram in which every node is associated with a variable of course, but we are doing an ordering of those variables. So, there is an index number that is associated with all the variables, and whichever is associated with the node, that index is now associated. So, the height is in the order of the indices, or we start with the root being at index 1 and the next level being at index 2 and so on. Okay. So, there is an index value associated with every node. The leaf node has the function values being 0 and 1, whether true and false. This is a binary diagram, which means that each node has two children, one is low and the other is high. This relationship holds, which is the index of a parent is less than the index of its children. So, because of that property, the graph is acyclic. And there is a Boolean function that is associated with these OBDDs. It is inductively defined as follows: if it is a leaf node, then that function is true or false depending on whether that value is 1 or 0. If it is a non-leaf node, then that Boolean function corresponding to the node V is composed in terms of the function associated with the low child and the high child. So, that is all that is there as far as the definition is concerned. We started off with one example where you have some function like that, c equals a plus b, but my ordering is ABC. So, I start off with a. Remember, the function ultimately is that I should be able to express this as a prime times something plus a times something, but we already showed that any function can be decomposed in that way. Shannon's expansion can be used to do that decomposition. So, once I do that, this is my function, but I have a prime times b c plus a times c. So, somehow that node has to be associated with the function b c, and that node has to be associated with the function c. So, we had gone through a traversal of this BDD structure. At the end, there is a Boolean function that is associated with every node in the diagram. Okay. So, and that function is composed using that simple rule. So, the function is 0 for all the leaf nodes, and as you go up the levels, you would compose more complex functions based on the values of the children. Just to illustrate that this is not unique, first of all, there is a dependence on the variable ordering. If you change that ordering to ACB instead of ABC, for that same function, this is the same function that we started off with, you would have a very different diagram. That should be obvious. Everything changes, the diagram itself completely changes if the second level is C instead of B, because those lower level functions would decompose differently now that I have picked up and expressed things in terms of C first rather than B first. In general, you expect a different structure. So, the way this evaluates to C times A plus B is these are still zeros and ones at the leaf level. You have a node with a b here, 0 leading to 0 and 1 leading to 1, meaning that the function is b prime times 0 plus b times 1. So, that is b. This with the 0 branch leading to 0, 1 branch leading to 1 is essentially C. This one with the C label here means that if C is 0, then the value is 0. If C is 1, then the value is b, and my function then is b c. Okay, this is b c and this is c. The function at the root is a prime times b c plus a times c, which gives me c times a plus b. It is the same function, but the structure is different here.
Each different one is a canonical form in itself.
This is not yet canonical. We will have to do something to make it canonical. We are moving in the direction of a canonical representation, but this is not yet canonical. You can see why it is not canonical. It is because that same function could be written in some other way. If you wrote it like this, then this is the way to decompose it, and this is the OBDD you get. But you could write that same Boolean function in some other way. We did not do any optimization here. There is no minimization, right? This is, I am just taking the algebraic expression that was given to me and just doing a straightforward decomposition. So there is no optimization here, but equivalently you could have written some other function, for example, involving a prime and so on, which is the same function, but the expression is different. You would end up with a different tree. You can easily see that by working out two different Boolean representations of the same function. For example, of course, one default representation is you just list out all the minterms. That would in general lead to a different structure. Okay, so first of all, if the ordering changes, then the structure changes. Now, let us look at some properties of these OBDDs. Two OBDDs are said to be isomorphic if you can find a one-to-one mapping between their nodes that preserves the indices, the children, and leaf values, everything. Right. So, if I have something like that, this is A, B, B, and this is 0, 1, 0 or some such. So, two such OBDDs would be called isomorphic if I can find an association. These are graphs, remember, in the general case. If I can find an association between these structures, so that for every node I find a corresponding node, for every edge I find a corresponding edge with the same label. Of course, leaf nodes similarly, right. If they are identical, not just structurally, but also in terms of all the annotations that we have made there with respect to the labels. I should have an A here if this was an A here, I should have B if there was B there, and the zeros and ones, everything should match. Then we say that these two are isomorphic. Isomorphic OBDDs of course would represent the same function, because there is a function that is associated with every node. So, if you have established that the nodes are identical, they have the same value, and everything that is rooted at that node, those are also identical, then the functions are also identical. However, the same function can still have different OBDDs. There is a need for us to make these OBDDs canonical. It is not yet canonical because the same function can have different OBDDs. We will see with an example. There is some advantage of this canonical representation. It is that if it has this property, then a Boolean function has a unique OBDD representation for that given variable ordering. If variable ordering changes, then canonicity is still not guaranteed in these data structures. How do you make them canonical? This is an interesting exercise. If you remove redundancy in the OBDD, then we argue that you have a canonical representation. So, let us see what kind of redundancy could be there in an OBDD. An OBDD is called a reduced OBDD, that is a reduced ordered binary decision diagram. It is a mouthful, but there are other extensions also to this. This is still intermediate in complexity as far as pronunciation is concerned. It does not help. ROBDD takes the same amount of time to pronounce as reduced ordered binary decision diagram, but writing it is easier. So, let us define what is a reduced OBDD. We start off with an OBDD and we say that it is reduced if a couple of properties are held. essentially we are saying that we will remove redundancy. So, what kind of redundancy could be there in a typical OBDD? This structure here, can you identify any redundancy?
Both the child of A are B.
Oh, both the children of A being labeled B does not constitute a redundancy. In fact, that's the way you expect it to be. Right, you have A and two B children are there, but this is some general function, right. This function is different. Let us say this is a function of B and C. This function is some other function of B and C. They would both look like this at that level. They would be different at the lower levels, but if you have, let us say, B plus C here and you have B C here, both of them will have B at the root. They are distinguished by what appears below them, but this by itself is not a redundancy if there are other things that come below it, because these functions could be different. In fact, this is how you expect that OBDD structure to be. This is not by itself redundant, but there is some redundancy in this diagram.
Last C.
Yes. What is the function associated with this node? With that node,
C is same.
the function is C, right. There is only one rule for evaluating it. You look at the two children functions and you compose the parent function. These two are isomorphic. The subgraphs that are rooted at the C's are isomorphic, and therefore the functions are also the same. This is C prime 0 plus C times 1, which is C. This is also C. Right. So, there is some redundancy there. What other kind of redundancy? Yes, there are two kinds of redundancy. So, if these two are the same, what does it tell us about B? It means that irrespective of whether the value of B is 0 or 1, the function here is the same. It means that it is independent of B. In fact, B should not even appear there. The reason it appeared there is that, well, that is the redundancy, but if you insist on finding the cofactors with respect to B, what will happen? The same function will appear as both the cofactor with respect to B and also with respect to B prime, and so you will end up with a situation like this. It is not invalid, the structure is fine, but this is not the minimal structure.
What would happen is we will have only A to C direct connection.
Right. So, I essentially need to get rid of this. First of all, I need to get rid of one of these subtrees because it is not necessary, they both represent the same function anyway. Right. But after doing that, after noticing that both the branches from B are leading to the same function, we can get rid of B and we just replace it by that structure. That is all that is there. So, an OBDD we call it reduced if you do not have a node with this low of V is equal to high of V, which is which example? Out of the two redundancies we identified, this property is which?
This is the
of
B one.
the B one, right, because the low function is the same as the high function. So, such a node should not be there in a reduced OBDD. That is one. Other property is there should not be a pair of nodes U and V such that the subtrees that are rooted at U and V are isomorphic. That is which example? That is this C example that we said there is duplication there, and if there is duplication I would like to get rid of one of them. These are the two redundancies. If I remove them, then you have essentially one copy of this function. B itself over there is redundant, so I remove that. The other B still remains, but this B is removed and I have this structure that is called a reduced OBDD.
AB plus AC or A prime, B prime. AC plus A prime, BC.
This was BC, right? This function was BC and that function is C. So, that is BC and that is C. So, I have A prime BC plus AC. Okay. This ROBDD structure is a canonical representation. Why that is the case, we are omitting the proof for this discussion, but all that we need to do is get rid of those two kinds of redundancies from an OBDD and you would have an ROBDD. Okay, since it is an important structure, let us try constructing a reduced OBDD from an OBDD. We will later on move to a generic algorithm for doing so, but let us look at what the strategy would be. You start from the OBDD bottom up, right, from the leaf levels. Right. You apply a label called an ID to each of these nodes. For every distinct function that we come across, we will identify a new label. So, initially I would have just the zeros and ones here, but for these two nodes I would give the same label because they are essentially the same function. So, I would apply a label, but my traversal is from the bottom up. So, these labels are also getting applied in a bottom up way. In the process at the end, that resulting ROBDD structure will have a subset of the original nodes. Why? Because two nodes with the same label means that one of those entire subtrees rooted at that node can disappear.
So, when we are applying the same label, we are only seeing the parents.
Only the children, right.
Not the parents.
Right. Remember, that is how the Boolean function for that node is defined. It is defined only in terms of its children. Its parents have nothing to do with that Boolean function itself. Right. So, two labels essentially correspond to the same Boolean function, and I would keep one of them. Anyway, what we are driving at is that the ROBDD is a subset in terms of nodes, at least it is a subset of the original OBDD, because we are getting rid of some of the nodes and edges. What we are retaining are the nodes with distinct labels, distinct IDs. If there is a repeated ID, then we would get rid of that. We would keep only one of them. And of course, if we keep one of those nodes, if we remove one of those nodes, it means that we remove everything that is under it, unless it is overlapping with some other parts. Essentially what it would translate to is you remove the node, also remove its associated edges, its children edges, at least that much you can remove. So, if that child does not have any other edge leading to it, then that child also gets removed. So, a point is you retain a subset of the original node. Some stitching up of the structure is needed because in the process of getting rid of nodes, you would end up with sometimes a node being redundant. Okay. So, if this label is 2 and that label is also 2, then what would be the label for the parent? We want to invent a new label in this labeling process when we come across a new function, right, that has not been encountered yet so far. So, I should apply 2 here, because the value of that function is this Boolean function associated with label 2, irrespective of whether b is 0 or 1, right. So, it is the same Boolean function that should be propagated to the parent, because what you have is b prime times whatever that function is plus b times that same function, right. So, this is nothing but f. So, I should propagate that same label up. At the end, I would have a structure that has a subset of all of these nodes. I would drop some nodes, but in the process I would get rid of some of the edges, and some stitching up has to be needed, because now I have to introduce a new edge. If I got rid of this and I retained this, I got rid of this node, then what happens to this edge? Right? I would have to reroute it to that node. So, that adjustment also I will have to make. Okay. So, this process of removing redundancy, assume that nodes with index greater than I are already labeled. We are moving in a bottom up fashion anyway. So, the higher indices would be processed first. Right. If you consider a set of nodes V with index I, what are those? At this level here, there are 2 nodes. So, here V equals A, or at least that node. here V would be the set of these two nodes. Actually, the structure can grow exponentially large as you go to the lower levels. You may have more and more nodes in the general case. Right. So, you collect all of those nodes. So, redundancy removal corresponds to essentially this kind of a check. I say if the label for the low is same as the label for the high child, then V is redundant. We are left with this kind of a function. That is V prime times G plus, so G is that function, and we essentially want to make G the value of the parent node also. So, how do you do that? Essentially in that traversal you just set the node of V to set the label for V to be the same as the label for one of its children, because the same function. Right. So, that is one redundancy, that is when that node itself is redundant. Other is if you find two nodes belonging to V, we are checking those nodes that all have the same index. We are talking about nodes with the same index. These are all nodes at the same level of the structure. Yeah. So, if you find a pair of them in which the low of x is the same as low of y and the high of x is the same as high of y, the same as means we are just comparing the label numbers. These are integer labels that we are assigning, and remember, a new number is assigned if a new function is arrived at. So, if I can find this, what does this mean? It means that the children are identical, children functions are identical. So, I found two nodes x and y. Actually, the nodes are called x and y. The indices are actually the same. If the index was 3 here, the index is also 3 here, meaning that it is the same variable. And this has labels A. If this left labels match and the right labels also match, what does it mean? The expansion would be the same, right, for both of these. Whatever that variable is, that is common, and it is that variable. So, it is a V is that variable. Then you have this situation of V prime times A plus V times B in both the cases. Yeah.
This thing that we said that for the same level we have, for the same level of the graph we have the same variable.
Right.
This is because we are considering the OBDD as of now. In
Yes,
the
yes.
ROBDD this is not the case. At the same level we can have different variables.
We still have the same ordering. If I get rid of a node, then this is still the third level, this is still the second, this is still the first.
But sir, when we have removed that node, then that C will come at the second level.
We will not.
We are constructing the ROBDD, we aren't yet the ROBDD yet, we are starting with the OBDD only. Right.
That's what I am saying, that this condition is true for the OBDD.
Yeah, yeah.
When we have reduced it to the ROBDD, this condition is no longer true then. That at the same level we have the same variables.
Same variables could still be there at the same, because the functions could be different. Let us say, so far I did not say it is reduced or not, but maybe it is the reduced form. Even in that form, if that my ordering was A, B, C, D, then I would have the root like this. And this would be some function of B, C, D, that would be some other function of B, C, D. B would still appear in both of them.
Ordering will even ROBDD.
Ordering is you start with A and then you have with B. So, just because these two nodes have the same label does not mean that the function is the same or that there is a redundancy, right, because this is some function of BC, this is some other function of BC.
If in the reduction process we get rid of one of the B's in the branch?
Then it is fine. The ordering is here, right, 1, 2, 3, 4, that is my index. Right. B is still associated with index 2, which means that it appears in the second level. If that other node does not appear in the reduced form, that is all right, this goes to the third level. The level is still the same, the meaning of index and level, these are still the same. It is just that the number of nodes at that level may go down as a result of any redundancies that we remove.
Is it possible that a complete level can go away?
It's possible. Right, you have a function of ABCD, but it turns out that it is actually independent of B. If you have B times C somewhere plus B prime times C, then this becomes C and the B level completely goes away. That is all right. The index according to our original function and its representation remains the same, but one level goes off and that is fine.
All the row levels come one level up and still that.
This is a graph structure. The level is only an association of a node with an index. You have a data structure in which you started off with 1, 2, 3, 4, but 2 is not there anymore. That is all right. This level anyway is only a visual thing, but what binds these is the assignment of that integer called index. You still have the property that the index of the parent is less than the index of its children. If that property holds, then the graphs that are rooted at x and y are isomorphic. You set the ID of one of the nodes to be the ID of the other. Right. Of course, you are processing them in some order. So, one of them would have been identified first. You created a new ID for x perhaps, and now when you are trying to create one for y, you will see that the one for x is already there. So, you repeat it instead of creating a new one. Going through the process for this example, I start off with the leaf level. Right. At this level, I can assign the IDs. There are two IDs. Let us just initialize our data structure with two labels, those are 0 and 1. Okay, so, for the 0 nodes we have a label 0, for the 1 nodes we have a label 1. These two both having the same label means that there is a redundancy. Redundancy means that ultimately I can get rid of that node, I can get rid of this node also, and instead route these edges to the distinct 0. You need only one 0 and one 1, you do not need multiple zeros because they are the same Boolean function. So, but as of now this is just a labeling exercise, we will do the pruning of the structure later on. Right now we are just assigning the labels to the OBDD. Pruning means getting rid, discarding the redundant nodes. So, already in this process we have found redundant nodes. Out of the 5, 3 are redundant. Right. So, but I do not remove them as of now, I am just proceeding with the traversal anyway. For the purpose of this illustration, we will look at the formal algorithm for doing so later on. That is more efficient than this. You can combine some of this. You can argue why first generate duplicate structures and then. So, but we will look at the more formal algorithm for doing so. This is still only a visual representation of the labeling process. So, I start off with the leaf structures, then I go one level up. This is a new function. Right. When I come to the index 3, the function computed here is c prime times 0 plus c times 1. That is a new function. It has not been seen as of now because our initialization was with just these two Boolean functions 0 and 1. Okay. So, this is a creation of a new function, a new label. So, the 2 is created. When I come here, I find that the redundancy criteria applies, and therefore, I will reuse that same label to the other. When I come to that node, that is a new label because this is a new function. So, with b as the index and a 0 as the left function and 2 as the right function, that is this, right?
Yes.
That function has not been seen yet. So, I create a new function. I come to this guy. What is the redundancy removal process? I look at all of these nodes in that level, at that level, and see whether I can find another node with the same Boolean function. How do I find that? anyway B is common for all of these nodes. Is common. So I try to find whether I already computed a function in which the index is B, which is 2 here, left child is 2 and right child is also 2. Right. Such a node is not there. So it is not redundant according to that criteria, the second criteria, but it is redundant according to the first criteria, because both its children have the same ID. That must mean that B itself is redundant. So I just propagate that ID to the parent. It is the same function. So these two redundancy criteria I evaluate. This one is easier because this is just a local travel. Just look at both of the children. Both the children have already been assigned labels. So it is a trivial check whether they are equal or not. If they are equal, then it is fine, then you already know that that node is redundant, you just propagate the label upwards to the parent. Otherwise, if they are different, then you would look at this level to find out whether there is another node that you have identified with the same children. So these are the checks that we perform. So 2 is propagated up and that is fine. Finally, when we move up, this is the creation of a new node, because this is the first instance of my looking for a function where A is the index. So index is 1, left child is 3, right child is 2. That is the first time it is occurring. So this is a new function. That is my labeling process. So if my nodes have been labeled from 0 to 4, it means that in that ROBDD structure that I am going to condense from this OBDD structure, I would have 5 nodes. Each label needs to be retained only once. So that is my structure. A is fine, this B is dropped, this entire subtree is dropped, that is what I have here, and that edge is instead routed like this to C.
Sir, we have just assigned distinct IDs
to the nodes in the OBDD.
function.
Right.
How do we determine out of, like, say there are 3 nodes having the 2 ID? How do
Yes.
we determine which one of them to keep and which 2 of them to?
Oh, as it happens, one of them would have been created first.
Okay, so the first one will be kept always.
First one is kept, the second one you would get rid of. But of course, this is assuming that we first constructed the OBDD and are extracting the ROBDD from there. Yeah, but we need not take that approach. We can actually build the structure by keeping these rules in mind only once, so that we construct only the OBDD. We do not necessarily first have the ROBDD, although the principle is this only.
My concern is that in that index with the C variable,
Right.
we removed the right hand side one and
Yeah.
it was alright. We could have as well computed the right hand side C1 first and then the left hand side
Right.
C.
Right.
And in that case, we would have kept the.
We would have retained the right hand side. It's okay.
And then we would have to add that edge because
Right.
it's not
Right.
existing.
That's all right. If we see this as a tree restructuring algorithm, it could be that I get rid of this. It could also be that I get rid of this and I keep this. In which case, that edge would now have to be rerouted to that sub. It's all right. Conceptually, it is the same. You keep one subtree, and for the edges that point to the other subtree, now you have to make them point to itself.
I mean, in the optimization, we just take it as it is. Like, if there is no edge, then we will add that edge, or we keep that
Okay,
in there also.
but why don't we just get to the form? We would not even want to construct the second instance. We do not duplicate. So the duplicate structure is there here for illustration, but the algorithm need not construct the duplicate structure at all. But how it does that, why don't we just take a look.
See, the other thing is, you said all the edges would have to reroute it.
Yeah.
There is no new edge creation. So this is one difference in the way one would want
Yeah,
to
there
run.
is no new edge.
You don't create a new edge.
Right. The destination,
You just
this is the directed edge, right? The source is still the same.
Same.
The destination would change. Okay, so let us look at the construction of that ROBDD itself. We would like to build it directly from the Boolean function. Given a Boolean function, we would like to construct the ROBDD directly, not necessarily first generate an OBDD and then do the reduction process, but the principle that we looked at for reduction is the same as what we will use in the construction. This relies on our maintenance of this search structure which we implicitly used in the redundancy removal, which is now I find a new what is essentially a triple that consists of a variable, that is the index, ID of the left child, ID of the right child. So, when I come across a new node in that OBDD, I want to check whether this thing of that variable, the left ID and the right ID, has this already been computed or not, has this been encountered before or not. Right. If it has been encountered, I should just reuse that label, I should not create a new label. That is the essential computation that we are doing. How do you do that efficiently? This is essentially an application of the hash table data structure, where it is a search that you want to perform. Right. That search, yeah, there are 3 elements of that, but that is okay. These all of these are integers.
That's fine, but I mean, I used hash table in our assignment and
Yeah.
it mapped one to the other, so there was only a pair. We can have 3 variables also in a hash table.
What are these variables anyway? So, I have variable left ID, right ID. All of these are integers. This is int, this is an index, right. So, that is an integer. This is also an integer, label is also an integer, that is how we have been using it. This is also an integer. You could think of this whole thing as constituting a new integer. Why not? Let us say there were 10 bits for this, 10 bits for this, 10 bits for this. Concatenate them, you still have one integer. Conceptually, this is just a concatenation of bits. The hash table works on such a principle. You have some string, there is a hash function that takes whatever you have and maps it, right. So, this is like a string or whatever, it is essentially a sequence of bits. So, now if that hash table has n entries, it will take this whatever this number is, maybe it is a 65 bit number, but that hash function would map it to one of the indices of the table. So, it does not matter too much what the data type is, that there are 3 entries there is only a conceptual thing. In terms of its implementation, you could as well treat them as a 1 bit string, and anyway that is what we do it. Hash table is used when you have a bunch of strings. What is an example? Suppose a compiler is trying to take an identifier and is giving the result, is this a keyword or not, right. So, it would take keywords like this, true, entity and so on, a bunch of these keywords, and it will try to find out quickly whether this string that you have given is a keyword or not, because the way it proceeds in the grammar check is different. How does it do that? A hash table is a good structure, because otherwise you it is expensive to do a string compare for every string. There may be hundreds of such keywords, right. So, they use a hash table structure which will essentially first evaluate each of these guys and assign them some hash. That hash function will take each of these strings and will map it to one of those indices, integer indices of the hash table. So, the way they do it is you first do the mapping. It is possible that more than one of those strings maps to the same index, and therefore, they have a linked list kind of a structure starting from each of those indices. So, when there is a conflict, when 2 elements map to that same index, then they will have a list structure, but it is still efficient because this list is typically not very long. If those hash function is distributing the indices well, then this may not be too long. So, essentially this translates to almost a constant time search. If the hash function was good, then it becomes like a constant time search. So, in that sense, having 3 different things is just a detail. You can see that what are these anyway? String of characters. So, we are talking about a string of zeros and ones on which that function would be applied. So, conceptually there is nothing different here. Yeah.
Basically, I have never learned about how hashing happens inside, but from your description, it feels that it tries to come up with an encoding mechanism where no matter how long the string you give,
Right.
it is quickly able to encode it into a integer map or some
That's
map,
right.
and then
That's right.
that conversion is fairly fast. That encoding
The conversion has to be fast. For us to argue that this is a constant time operation, you can't take too much time for that. You evaluate those hash functions in terms of the properties of how nicely they distribute given whatever the application is. Essentially, it should not be of the kind that there is space in other locations. Other locations are empty, but this linked list is unnecessarily built up on one of them. It means that large number of conflicts are there. That is an example of a bad hash function, because it translates to essentially how will you search in the linked list, it becomes linear time search again. So, the property that a good hash function will try to incorporate is that it is as unpredictable as possible with respect to the mapping. It randomizes the mapping to the extent possible. So, anyway, I maintain the hash table here where I give a variable ID. So, these are all integers, and I have one entry here in the hash table for every distinct node in the OBDD, which becomes every node in the reduced OBDD. When creating a new ROBDD node, I will first check if it already exists in the unique table. How do I check? I run this search. Right? I just do this search in the hash table, and if that search is true, it means that this node is already there in the unique table. Right? There is no need to create a new one. So, this is a constant lookup time almost that is usually the case for these hash functions, and a new node is created in the unique table if it was not there. If it was there, I should just reuse the node itself. So, let us just quickly develop the algorithm itself. The strategy is what we just said. So, our input is a Boolean expression that is there in some format. That format let us ignore for now, but it is an algebraic expression. It is able to take a sum of implicants or sum of minterms or whatever it is. So, that Boolean expression is an input. So, if I write an algorithm build and that function is an input for me, what other input would be there? To the BDD construction algorithm, I have 2 inputs. One should be that function itself, other should be, yes, other is the ordering. The ROBDD is dependent on the order. If it is ABC, I get some ROBDD. If it is ACB, I get a different ROBDD. So, that index, which is an integer, that also has to be an input to the function. What it should return is a node of the ROBDD. If you have a function f of a, b, c, something like that, and that order is a, b, c, then I can call that build function with a or 1 as the index first. Okay. This is a recursive definition. We can build it inductively using recursion in the following way. So, that function, whatever, if it is a plus b prime c and so on, that function is provided here as an input, and maybe that first one is provided as an out as the second input. So, how do I go about building this? Yeah, the idea is I should use the Shannon expansion and derive the cofactors. Cofactors, so the building can be bottom up, even though the traversal is top down, because we start from the top level, In fact, it is easier to build that structure in a bottom up way. The algorithm can do the building up, can actually do the traversing top down, but start doing the construction bottom up in the following way. Let us handle the leaf cases first. So, I create these two elements first, right, 0 and 1. So, I insert them into my unique table. That unique table is the hash table into which all the nodes are being inserted. So, 0 and 1 are already inserted, pre-inserted before the function begins. So, I can say if that function itself is 0, then what should I return? So, this is V 0, these two nodes are already there. So, if the function that is passed to me is 0, then right, I should just return V 0, that node is already there. Okay. Else I say if f equals 1, then I should return V 1. If it is neither 0 nor 1, what do we do? Then it means that it is an intermediate node somewhere, right.
We need to create with that literal that we are.
So, the index is what is already given to us, right, that is the variable. Okay. So, let us say that corresponds to variable v. Then what should I do? The variable is given to me, function is given to me, what do I need to do?
Put the edges from there.
Right now nothing is there other than these two leaf nodes. I have to construct them, of course. So, how do I construct them?
We can't put the edge until we evaluate.
Until the children nodes are there, we can't put the edges, right. But as of now only these two children nodes are there. So, I somehow have to use a recursive process until I end up with the leaf nodes, right. So, let us say I reach the leaf nodes, then at the next level what do I do?
I add the index to the hash map and the edges according.
So, these are the two base cases of the induction, right, that is already taken care of. If it is not one of them, then it is an intermediate node, and what I could do is, this is an expression, right, Boolean expression. I can determine f v, this is also given, the index is also given, which variable I know. I can return f v and f v prime, I can compute them in terms of whatever tool I have given. This expression is given to me in some way. Using that I should be able to drop all the a primes or drop all the a's and get f v and f v prime from there in this format, in that expression format, whatever that expression format is. So, this is a local computation I can do of the two cofactors, I get some other two expressions. Then what?
Then I recall this.
Then I call this build routine again on those expressions. Right. So, I should have build, now I give f v, the cofactor of f with respect to v, with what index? Cofactor of f with respect to v does not have the variable v anymore. I should give index plus 1, right.
Index is
Index plus 1. Index corresponds to v, index plus 1 corresponds to the next node, and both of its child functions would be in terms of index plus 1, index plus 2 and so on, the rest of the subtree, right. So, these two I should, so let us say I say low is equal to this, the other subtree, so this is high, this is with respect to v prime, and the index also being index plus 1. So, this would return the nodes here, right. What do I do after this? So, this is a recursive call, you understand how the recursive process works. If this it turns out is another expression, then it will call the same function again, and the termination of the recursion happens when? Right here, right. When. So, you can see that in this forward pass there is no construction that is happening. We are just invoking the recursion all the way down until we terminate, we reach the leaf, but the moment we reach the leaf, it means that we have enough information to build the lowest level of nodes, right. So, then these two are already, so in that case that BH and BL would be the my V0 and V1. This would return V0, right, at some point, at some other point for this leaf I would return a V1 instead. So, that is what would be captured here as the left subtree and the right subtree. These are the node type that is being returned. So, I got these two nodes. In the special case at the leaf node, this BH and BL essentially are V1 and V0. But in some intermediate case, it would be some two nodes that correspond to the left subtree and the right subtree, whatever the Boolean functions are. So, then what do I do? Essentially, I have my two children now. Then what?
And I add the edges, and that mapping thing has to be done now because now.
So, now that I have these two functions, I can now search in my hash table. These two are already there in the hash table, remember we initialized them. So, now I want index, because that is the variable in terms of which I am going to compose my new function, and these two BH and B, think of this as the tuple that we are searching for in that unique table, right. This is what we are searching for in the hash table. So, we are looking for, is there an entry with index as the variable and BH and BL whatever they are. If it turns out that they are V0 and V1, it is fine. We are, if this is C and this is V0 and V1, then we are essentially looking for C V0 V1, right. Otherwise, it is whatever it is. So, it means that the first time you are looking for C V0 V1, you would not find it, you would insert it. But the second time you are looking for the same thing, you would find it, and therefore, there is no duplicate structure that is created, you would just return the same label.
Same level.
It's the strategy is clear, that is all that is there to this algorithm, there is nothing else. The algorithm is clear. There are those two redundancies that we had. If you find it, then you do not build a new one, corresponds to which rule? There are two rules for redundancy removal. One of them is that the two children are the same. Other thing is that the two nodes are isomorphic. Yeah. So, this thing of looking up in the hash table to find whether such an entry is already there is implicitly doing one of those redundancy checks.
So it is checking at the same level.
Right. It is checking that isomorphic subtrees. Right. This is the isomorphic subtrees. So, this is happening just by virtue of us using that hash table data structure and making sure that if something is there, then you do not create it. That is basically the duplication avoidance. What about the other rule? So, we will say that continuing this, if this was V, then you return V. You looked up in the hash table, you got V, either because this is the first time it was created, a new V was returned, or if it was already there, then an old V was returned. You can see that this node is actually nothing but that label. You think of it as nothing, just that label, just okay. So,
this shouldn't we check for BH is equals to BH?
yeah, so that is the other one. This is just we were going with the flow of the search, that is why it was introduced first. I return the V here, but that other one has to be checked, which is, are the children identical? How do I do that? In fact, there is enough information. These two, I just compare the two values. If they are equal, then in fact, I should at here itself, even before doing the lookup, there is no need to look up the hash table in that case, because this is returning the value, right. The call to build is returning the right values. If both those values are equal, then I should return
The same index should be propagated further.
I got B B L equals. Remember, this build call is going to propagate things further. That's what it was doing. BH equals another build, right? So essentially, this was f of v with an index plus 1, f of v.
It is returning the node name, it is also returning the node name. If they are equal, then you should just.
You can get that with another hash table if you want.
Right. Now, our check was if BL equals BH, then it means that I did the traversal of the two cofactors. It turns out that the two cofactors are identical. In fact, the structures corresponding to those cofactors have already been built and designed and inserted appropriately into that hash table as of now. So, what else remains to be done for the parent node?
We need to send the one of the information of the BLBH, either of them,
Yes.
that return either BL or return either BH. Right. This is what will
Right. This is node with V, right? So, I should just return
either of the.
that's all, because there is nothing new to be done. In fact, I am going to drop this node, right? I have to drop this node. So, I should just propagate the label of the child to its parent. Right. So, that is all that we do. Otherwise, I should do the unique table search that is it. These are the two redundancies that are identified. One is this simple check to find whether the two children are equal. Other is the lookup in the hash table to make sure there is no duplication. So, we do not create the duplicate entries. That is what my algorithm is. That is the expression, two nodes, that is what we already saw. This is the termination condition. P is the variable corresponding to that index. You call the same two routines, these are the recursive calls on the cofactors with the index plus 1. Okay, now you are doing this check to find whether the two children are equal. If yes, then you return one of them. Otherwise, you return whatever that unique table lookup is giving you. Okay, you create the node if it does not exist. If it does exist, then you just return the node. There is no creation. We can go through a construction example, but hopefully the logic is clear. Suppose I start off with this is the same function that we used in our examples. This is 1, 2, 3, 4. These are the index values that are sent. So, the ordering is ABC means that A is 1, B is 2 and C is 3. So, this call at the highest level just results in a recursive call. There is nothing further that is done. You can't do anything more until you return from those recursive calls. So, you first compute the cofactor of that function with respect to A, you get C plus BC. That itself is also a complex expression, you can't do anything, you have to call the recursion further. So, C plus BC, again you take the cofactor with respect to B. Now, 2 is B, right. So, you take the cofactor with respect to B, you get C, and now you call with the recursion this time with 3, which is C. Fine. With C, now again you do the same things. You take the cofactor of C with respect to C, you get 1. The cofactor of C with respect to C would be you replace C by 1. So, you get 1. If the cofactor with respect to C prime is 0, you replace C by 0. But this is the termination of our recursion, because you are sending a 1 there, which is true or false. There is enough information. In fact, these are the nodes that would be returned from that level of the recursion, the innermost level, right. V1 is returned. From here, V0 is returned. So, that means that that much is done. I am back at this level of recursion where C was my expression. I would now look for a node in which C is the variable. So, the index is 3, left child is V0, right child is V1. Such a node is not yet there, because my table so far has only V0 and V1. So, a new node V2 is created with that function. So, that is my ROBDD so far. Okay. I return from here with respect to B, you get C, that is what this was, but when you take the cofactor of C plus BC with respect to B prime, what do you get? You also get C. So, essentially this is another call, we can do something about it. This is the same thing that is called twice, that is the same logic all over again, because that function is again C. Because V2 was already created corresponding to that function C, now at the end of this recursion, in fact, what do I have? I have C's index is 3, I have V0 and V1, that is my tuple. Right. So, this was inserted the first time, that was my V2. Second time when I look up, I will find this index in the hash table. So, I also return V2, which means that as I come back to this level here, I find that both of these cofactors are actually same, both are C. Then what do? The V2 is actually what is propagated at that level itself, because both of the cofactors are the same. So, therefore, both the children are the same node, both the children are V2. So, the parent also would return V2. Okay, that is one. Okay, so, this is the recognition that L equals R. So, L equals R, I would just return V2. That is part of the recursion done. This is one of that A plus BC. Then I can go down the A plus BC with respect to A prime. I would get what function? No, BC, because the first one would go away, I would get BC. That is what this is. Similarly, I would take the cofactor of BC with respect to B, you get C, which is what has already been done. Cofactor of B with respect to B prime is what? Cofactor of BC with respect to B prime is 0. So, I would call this returns 0. So, nothing new here, but when I come here, now I am looking for a node in the hash table with B as the index. So, 2 as the index and V0 on the left and V2 on the right. Such a node is not yet there. So, I create a new node V3, that is essentially part of my new ROBDD that got created. Once I am done with that, I return from all the recursions at the highest level. I am looking for a node with A as the variable, which is index is 1, and V3 and V2. So, from one I got V3, from the other I got V2. So, the two children are V3 and V2. That is what I am looking for, that node is not yet there. So, I would construct this, then this becomes my ROBDD. Any questions? The basic algorithm is fine, and the way we traverse through the example illustration, that is also clear, right. In fact, that hash table has within it everything that I need. I do not create a separate data structure, graph or anything, because the children are there, you just need a pointer to the top. From there you know what the children are, and therefore, you actually have the entire structure implicitly constructed in the table itself. There is no need to maintain any separate graph, node, edge or anything. We have been calling it a node, but in fact, you do not really need a separate graph structure. The result of this traversal, in fact, everything is encoded in that hash table itself, and that is the BDD. The representation of the BDD, even though we are showing all these nice diagrams and colors and nodes and edges, you actually have a more boring table, but it is embedding everything that we have been talking about. It is a very powerful structure. It's BDD, it's the ROBDD that we are talking about. What to do with it? There are lots of interesting applications and operations that we can perform. We'll look up about it next, but the basic representation is just this.